Hi student, today's topic Latin square design. Now what is the Latin square design? In RBD, whole of the experiment area is divided into relatively homogeneous group and treatment are allocated at random to units within each block. Randomization was subjected to one restriction within blocks, but in field experimentation it may happen that experiment area exhibit fertility in strip. Cultivation might result in alternative strip of high-low fertility. RBD will be effective if the block happen to the parallel to these strips and would be extremely inefficient if the blocks are across the strips. Initially, fertility gradient is seldom known. A useful method of eliminating fertility variation consists is an experimental layout which will control variation in two perpendicular directions. Such a layout is a Latin square design, in short LSD. Now the next point is layout of design. In field plot experiment, the Latin square is usually laid out in the conventional square with the rows and columns corresponding to possible fertility trends in two directions across the field. In other types of experiment, the rows and columns may be made to correspond to different sources of error, as in an animal feeding experiment where the column groups may correspond with initial weight and the row group with age. Now the third one, standard Latin square. A Latin square in which the treatment say A, B, C, etc. occur in the first row and the first column in alphabetical order is called standard Latin square or a Latin square in canonical form. For 2 into 2 or 3 into 3 Latin square, only one standard figure exists, like as AB, BA. For 4 into 4 Latin square, 4 standard square are possible given by like as A, B, C, B, C, A and C, A, B. Okay. From a standard Latin square, we can generate a number of Latin square by permuting the rows, column and treatments which are known as transformation sets of Latin square. The number of square that can be generated from a standard m into n Latin square by permuting the rows, column or letters. These are not necessarily all different. If all rows expect the first and all columns are permuted, we generated m factorial into m minus 1 factorial. Total number of possible Latin square of order m into n or m cross m equals to m factorial into m minus 1 factorial into number of standard square. Now the following table the total number of m cross m Latin square that can be constructed for different values of m. So we draw the table. Four column. Now here it is m, right here number of standard squares, and here m factorial m minus 1 factorial, and here write total number of Latin square, that is m factorial m minus 1 factorial into k. Here write 3 4 5 6, and here 1 4 56 and 9 4 0 8. Here 6 into 2 equal to 12, 24 into 6 equals to 144, 120 into 24 equals to 2880, and 720 into 120, that equals to 86400. Here 12, 576, 161280 and 81285 1200. Thus we see that the total number of possible arrangement increases very rapidly as the value of m. The size of Latin square increases, thus making it rather impossible to tabulate all such agreements of higher values of Fishers and Yates have tabulated some standard Latin square in of Fishers and Yates statistical tables for biological, agriculture and medical research. Now the next topic is analysis of convariance, which is ANOCOVA. The basic object of design considered so far is to make the treatment comparison with the greatest precision by reducing the experimental error through the powerful tool of local control. Analysis of convariance like randomized block design or Latin square design in a technique of increasing the precision of the design by reducing the experimental error. ANOCOVA is the technique in which it is possible to control certain sorts of variation by taking additional observation on which of the experimental units. Let us suppose that in an experimental y is response variable and small x is the another variable which is linearly related to y. Moreover, x cannot be controlled by the experimenter but can be observed along with y's. The variable x is called covariate. In ANOCOVA, we adjust for the variation in response variable y for the linear regression of the independent variable. If this is not done, then the error mean square will be inflated due to the linear effect of x, thus making it difficult to detect the true difference in the response variable. ANOCOVA, its ANOCOVA producer is a combination of analysis of variance and the regression analysis. Wherever it is possible to make additional observation, one or more of the variables from each of the experimental unit in the design along with the response variable under study, the ANOCOVA technique has proved to be useful in many areas of research. We give below some illustration for the use of ANOCOVA by identifying the response variable y and concomitant variable x. Number 1. Suppose we want to compare the effect of some ration the weight of animals. We can analyze the data by performing ANACOVA by regarding y, the final weight of animals taking the ration after a specified periods as the response variable, and x, the initial weight of animal at the time of starting the experiment as the concomitant variable. To ensure that the real difference in the final weight y are due to the ration, we must adjust for the linear effect of the initial weight x on y. Number 2, suppose we want to compare the difference in the strength of the filament fiber y produced by different machines. Obviously y depends on the thickness of the fiber. Thicker the fiber, stronger it is. The effect of the thickness x on the strength y can be eliminated by the performing ANACOVA between the response variable y and the concomitant variable for testing the difference in the strength of the fiber produced by different machine. Number 3, in plant breeding experiment, suppose an equal number of seeds are sown per plot, but at the time of harvested the final number of plants in which plot will be same due to certain reason and will vary from plot to plot. The yield y of a crop from the different plots may depend on the number of plants per plot. To study the real difference between the yield, we adjust for the linear effect of the number of plants per plot by performing ANACOVA by regarding the yield per plot y as a response variable and the number of plants per plot x are the concomitant variable. And number 4, and this is the last one, suppose we want to compare the different method of teaching like classroom, lectures, corresponding courses, online teaching, etc. etc. By observing the score of the student, all of whom that take the some final examination, the variation in the score may not be simply due to the different method of teaching but also due to the intelligence quotient level of the student. Hence, the proper way to compare the different method of teaching will be adjusted by the observed data for IQ of the student by carrying out the ANACOVA by taking the score y of the student as the response variable and the IQ of student as the concomitant variable.